Hello, hello, good morning, good afternoon, and good evening. Welcome you again to this World Large River and Delta System Source to Sink webinar series. Today, we are very happy to invite Professor Jaia Syvitski give a talk about Anthropocene source to sink study contributed to Earth system science. So before I introduce Jaia, I would like to mention our next week's webinars. Next Wednesday, we will have Professor Edward Tipper from University of Cambridge. He will be the first person begin to talk about the geochemical part of the source to sink, particularly focus on the reduced silicate weathering, the feedback from the world's largest rivers. That will be very interesting talk. So the time will shift back to the 9 a.m. and 2 p.m. in London and 3 p.m. in Paris. And also next Friday, we will have Edward Anthony, the chief editor of Meteorology from France, and he from the European Center of Research Center of Geoscience and Environmental Research Center. He will talk about river deltas and longshore sediment flux, and particularly as an example case study of the Amazon, Mekong, Irrawaddy, and the Niger deltas. So please mark your calendar next Wednesday and next Friday. So coming back to our webinar series. Okay, Jaia Syvitski. I don't think I need to say too much because Professor Syvitski is such an icon and everybody know him and know his her work. So Jaia received the doctorate degree from University of British Columbia, UBC, back to 1978. And 1995, I believe he moved to US as serving as director of INSTA. Then he has more than 500 publications and also 65 peer-reviewed books, and also served so many leading roles in the large international project. And one thing I want to notice, pointed out, from 2011 and 2016, 5 years, Professor Syvitski chaired as the chair of the IGBP International Program. So, and as you can see from a Google Scholar citation, his citation is almost 30,000. I think there's really something. So personally, Jaia is my mentor, my friend, my buddy, and also my role model. So he helped me a lot, encouraged me a lot all the way in my career. So today, we are very happy to invite her to give us an overview and also some review talk about Anthropocene. So Jaia, now it's your turn.
Good morning, everyone. Let's see, there we go. Good morning. So today, I thought my conversation with you today would be to introduce the concepts of the Anthropocene and Earth system science, and how source to sink studies can play an important role in that. And I'm making the assumption that not everyone knows about the details of the Anthropocene or even Earth system science. And so, but I assume you're all experts in source to sink. So that's how I'm flavoring this conversation. Okay, and how do I, there we go. There we go, okay. Oops. So the Anthropocene has a thesis, and the thesis is that humanity's ultimate...
We haven't seen your screen. Please share your screen.
Oh, okay. Okay, there we go. No, not that one. means I have to put my glasses on. Back to meeting. That sounds about right. Share screen. That sounds about right. Share. Is that anywhere closer?
Yeah, you're getting there.
Important presentation. Yeah.
You are sharing your screen. So is that sharing it now?
Yes. Flip on the first page.
Okay. So the first page is a picture of the US and its cities and its transportation routes. Okay, so back to this thesis. So the thesis is that humanity's alterations to Earth's planetary system include changing the very nature of how the surface dynamics of the Earth have been altered. And it's not that humanity has not been around for a very long time, but the changes have reached a scale where Earth's energy balance has changed, terrestrial marine ecosystems have changed, and in our case, geomorphic and sediment transport processes have changed. So that's the thesis, okay? And what's important about this thesis is that they have led to sufficient physical, chemical, and biological changes to the Earth's stratigraphic record, that's important, to justify a new geological epoch. So now you have stratigraphy, you have Earth system science, and you have the Anthropocene. So where does source distinct science studies come in? Source distinct science is about where things come from, how do they get from point A to B, and where do they end up? That's source distinct science. And they're into the interactions of all of these energy balance systems and ecosystem studies and transport studies. So I think these two slides let you know a little bit about how source distinct can fit in. And my presentation today will walk you through some of the details of this, because at a detailed level, most sedimentologists wouldn't be that familiar with all of this, okay? So that's my goal. So there are three main anthropogenic drivers across the Holocene and into the Anthropocene. And if they relate to humanity. So, and the Anthropocene is basically a new geological epoch where humanity is at the front. So you have to look at, well, what are the drivers of humanity? And there are three that the community has identified: population, their energy consumption, and their productivity. So here's a plot across the Holocene and into the Anthropocene. And in this study, we're assuming the Anthropocene begins in 1950. And so I'm showing this data, and you can see where 1950 comes in, and you can see that there's some big state changes in these drivers around that time. And so that would mean that the Holocene, which is the last 11,700 years, it had more natural drivers. And those drivers are like Milankovitch, the planetary orbital impacts on climate. But what may be unfamiliar with you is that some of these key environmental drivers that relate to population, productivity, and energy consumption, they track really closely with these environmental factors. So for instance, you can see that it should be no surprise that global reservoir capacity of large dams is almost a linear relationship with global energy. So duh, makes sense. atmospheric CO2. Okay, again, a very linear relationship with global energy. And I think we all know that from what you've been reading in the newspapers about global warming. Plastic production tracks similarly with global GDP. Cement production tracks with global GDP. Copper production tracks almost perfectly with human population. Ammonia production, fertilizer, tracks almost perfectly with human population. So you can see that major environmental factors also track with these human drivers. That's part of the Anthropocene thesis. So that was across. So we've been talking about the Holocene, the Anthropocene, but let's look a little bit about the transition. You know, when did the Anthropocene occur? I mentioned 1950, but let's look at some of the data. Well, for environmental parameters, we have identified, of course, these three drivers: human population, energy consumption, and environmental parameters such as GDP. So let's go back to human population. Well, what could lead to a source to sink signal? Well, megacities. There were no megacities in 1900. In 1950, there were but two, and you can see the acceleration. Well, let's look at human energy consumption. Well, for fossil fuel consumption, you can see that there was very little back in 1900, which is only 120 years ago. And you can see how it shot up by 1950 and skyrocketed since. And of course, with that are the CO2 emissions, how we detect the changes of those emissions in the atmosphere, and the other greenhouse gases, nitrous oxide, atmospheric methane, and how they've shot up. And of course, because of that, with global warming and the trapping of solar energy, we have sea level rise, where in this case, we've normalized it to 2000. So you have a negative before and a positive after. And land ocean temperature index, again, with that normalization and the skyrocketing temperature. So with the environmental parameters, and we'll get to how these mean in the source to sink in a moment, but let me just go through some of this. So you have this global productivity, and you can see this. We're at 74 trillion in 2015, and you can see how it various items below it reflect that. So we have motor vehicles, and so almost none in 1900. Now, you know, over 1 billion. The important thing here is what's behind this from a source to sink. So for instance, there are thousands of tons of sand and gravel that go into the kilometers and mileage of roads from these motor vehicles. And that is part of, well, where's the sand coming from? The number of dams in thousands, you can see that skyrocketing up. It's mostly all since 1950. And they trap sediment. So that's, again, part of the source to sink. Fresh water use. You can see how that skyrocketed up. And you can think about, oh, how does that impact source to sink studies? Shrimp farming, I think you know from basically what people have been giving you in these lectures and other lectures, that shrimp farming has a great impact on deltas and their sinking. Plastic production. Well, yes, that shot up incredibly, of course, since it's a more recent invention. But look at the millions of tons per year. This plastic is showing it's melting out of glaciers now. We can define it in snowfields. We can get it in soils. It's a huge signal. Cement production. You can see how that shot up. We talked about ammonia, aluminum, copper, mineral species. Mineral species. There are only 5,300 mineral species that were natural over the last 4.3 billion years. But now we have over 170,000 mineral species. Mineral species, not synthetic minerals that humans have developed. Iron and steel, sulfur, salt, gypsum, others. Just so, okay, then you can lay this all out on the various stratigraphic defined ages of the Holocene. There's the Greenlandian, Earth-Grippian, Megalayan ages. They're all between 3,500 and 4,200 years in interval duration. And all of the numbers you see here are interval averages. And when you look at the Holocene, you can see that it was warm at the beginning, and then it wasn't, and then it was cooling down a little, but very little change in climate. If you look at sea level rise, well, we were getting out of the ice age, and the sea level was going up rapidly at the beginning, and then it leveled off, and then it started to approach zero. These two units, these informal units, pre-industrial and industrial, they're part of the Megalayan. And so we can see that the pre-industrial had the lowest sea level rise in the Holocene history. And you can look at human population, one of the drivers, and you can see that how it's skyrocketed. And if you wanted to know how that's translated into growth rates, the growth rate in the Anthropocene of humans is incredible, 1.6% per year on average. And the primary sources of humans weren't that much, you know. We were dealing with fire, muscle, animal muscle. So there was just, and at the very end of the Megalayan, we had coal, we had whale oil, and of course we had streams. But it wasn't until we got to the industrial that we started to really kick in some of these incredible energy sources. And so the per capita energy, so now we're just looking at what on average on our planet, what did humans use in terms of energy consumption. The Holocene had a small energy consumption per human because most of our time we were spent looking for energy. We were looking for fodder for animals and food for us and things like that. But with fossil fuels kicking in, our energy consumption is just really shot up. And so that the total interval energy is now such that in the Anthropocene, we've used more energy in the last 7 years than in the last 11,700 years. And most of that energy consumption in the Holocene of this, 14.2, is seen here around the pre-industrial and the industrial. So 35% of the Megalayan energy consumption was in the last 100 years. And similar with productivity. So now let's get a little closer to our science. Now that you know some of the economic drivers and the consequences, let's look at some of these. So the first thing is Earth's oceans have stored 436 zettajoules of solar energy since 1871. They trapped this solar energy through increases in anthropogenic greenhouse gases and warming-induced water vapor. Now that 436 zettajoules, that's more than an order of magnitude more than humans consume themselves. In other words, we are burning an incredible amount of energy for our own consumption and needs and productivity and population. But it's this greenhouse gas trapping that could really be a force multiplier. And because of this force multiplier, that's not occurred at any time in the Holocene or previously. And so you have the oceans warming up and to great depths, greater than 2,000 meters. And that's from this trapping, soaking up the heat, solar energy. And even atmospheric temperatures have increased. It's harder for the atmosphere to increase temperatures, I think you all know, simply because most of the energy gets soaked up by the oceans. So when you have a 0.9 degree since 1950 temperature increase, that's simply incredible and scary and existential. The sea level rise has been going up rapidly as the Earth's oceans have heated up. And don't forget, more than half of, or about half of the increases in sea level rise is all because of steric effect, the thermal energy storage. And we're now accelerating at 3.7. So we've already passed 2 of the 3 ages of the Holocene in terms of sea level rise. And as a consequence of this, Greenland and Antarctica have both lost 5.5 teratons of glacial ice. They're losing it at between 125 and 140 gigatons per year. And the sea ice volume is 300 cubic kilometers per year loss, which roughly translates to about 275 gigatons per year. That's in the Arctic. And this year and the last year have seen the largest record of Antarctic sea ice loss. And with the partial pressure exchange between the atmosphere and the oceans of gases such as CO2, you can get the ocean soaking up the CO2, and because of that, their pH is declining at an incredible rate, and because of that, it's scary for all carbonate and organisms that are pH sensitive. And most of the oceans, the organisms are all pH sensitive because the oceans have been around for a very long time, unbelievable buffer, and now they're changing. So all the organisms are unprepared from an evolutionary point of view. So if you were to break this down into 3 units, the global Anthropocene environmental parameters that are having a 200 to 300% variance compared to the Holocene include temperature in the ocean and atmosphere, the greenhouse gases in the atmosphere, methane, CO2, nitrous oxide, global reactive nitrogen, metals in the environment, and there's a whole list there, such as mercury, phosphorus, sediment transport, terrestrial soil loss, and terrestrial marine biomass loss. And that's between 200 and 300 plus 400, 500% variance compared to the Holocene. But then there's another list where there's order of magnitude changes, like how much energy we produce, or the mineral species that are distributed around the world, concrete or aluminum metal, or species extinction, declines in river runoff, increases in coastal hypoxia, upstream sequestration of sediment. And then there's that last list, changes without any Holocene precedents, such as a more acidic and warmer global ocean. Global dispersal of new materials, such as fly ash, persistent organic pollutants, plastics, pharmaceuticals, ceramics, aluminum metal, radioisotopes. And then there's marine and terrestrial biodiversity. It's just the Holocene has nothing compared to the Anthropocene. Globally distributed invasive species are everywhere. Earthquakes now can have an anthropogenic impact. Well, that of course could not have happened and did not happen in the Holocene. So I hope that sort of gives you a little bit about what this Holocene, this Anthropocene is all about. Now, along the way, as this science started to develop, Earth system science, that's the International Geosphere Biosphere Program that I once chaired, that's been around, that was around for more than a quarter century, 25 years. They basically developed Earth system science. And Earth system science talks about the interconnectedness of nature at the planetary scale. So you can't have global warming exist without biogeochemistry because of all the gases and the impact on plants and the atmosphere and things in the ocean and all this biogeochemistry that goes to the heart of the interconnectedness of nature. And for those of you who are stratigraphers, you would know already, but for those who are more sedimentology oriented may not, stratigraphers examine records in the sediment rock record to identify changes of state in the Earth system. So there's a wonderful connection between stratigraphers and Earth system science that's been known for a while. So when we look for markers and other things in the rock record, we're only doing it for one reason. We're looking to see what are the big changes. When we go back in the Earth system time, where do we see these big jumps? That's stratigraphy. That's what Earth system science is all about. That there is this planetary scale, and I think a lot of people get caught up in very regional stories, very provincial or local stories, which has nothing to do with the Anthropocene. Anthropocene is big stuff, big picture. It's hard to change a planet the size of the Earth. That's what it's about. So when you're looking for records of the Anthropocene, you might look at all the lakes around, and you may be looking for changes in a marker such as the isotopic nitrogen-15. And if you do that and you look at these lake records, well, if you look at these pictures down in the middle of the screen, you can see the color change. Well, that's a given sign that there's something big it's happened. That's all the Holocene and all of these rock records, sediment records. And if you look at the actual dating and values, you can see that the inflection occurs someplace around 1950 in all of them. So again, you're looking for planetary scale records of planetary scale changes. And you would look for, of course, places that you think would stand a good chance of a more permanent record, such as marine anoxic deposits. Well, it turns out that marine anoxic deposits really reflect to a large extent population density of humans and all this carbon they throw into the marine system, you know, nitrogen and carbon that basically make the waters anoxic. And they're the perfect places to look for these signals. And so you've got, of course, the impact. So we now have humans and their need for food and the development of reactive nitrogen and the release of this overuse of nitrogen that then goes down our streams, creates the dead zones, creates the anoxic zones that could lead to locations where you can get a stratigraphic signal of the Anthropocene. So those were one or two examples, lakes and anoxic basins. But if you looked at environments, this is what stratigraphers would do. They would say, well, what are all the environments that we may find signals? And here's on the left-hand side of your screen, you would have anoxic basins, corals and bivalves, estuaries and deltas, lakes, peats, peatlands, ice, caves, trees, and then across the top, you'd be looking for markers, and these would be markers that were chosen to reflect the Anthropocene. So it may be radioactive stuff like plutonium-239, it could be carbon-14, it could be any number of these signals. And this community, the Anthropocene Working Group that I am also a member of, you would populate this with, do you have a record of the Anthropocene? What signal are you seeing it in? Well, what date do you see this inflection? And you would come up with some sort of background story in relating the human drivers, productivity, energy consumption, and population to these environments and markers, and you complete the story. And that's where we were writing this paper that got a lot of press on how we functionally can see the Anthropocene being distinct from the Holocene from a stratigraphic point of view. So you're more sedimentologists, so I thought I would introduce you to a little bit more on the sediment side. And the only way I can do it is talk about gigatons. And so if you take the Great Wall, and it has a certain length, certain height on average, certain width on average, and you get a volume, you get some density to the bricks and stones, and you'll get a weight, and that mass is 0.4 gigatons. So you can say that 1 gigaton is 2.5 Great Walls of China. And I do that because, you know, for the next few slides, I will talk about gigatons, but you may not know sort of what the mass of that gigaton is. So I think it's really important to have this in mind. So let's start with the Quaternary versus Anthropocene S2S fluxes. Well, Quaternary sediment masses, this is a wonderful study by Bill Hay, one of the preeminent scientists of all times, but also in my lifetime and a hero of mine. You know, he's mapped out globally the Quaternary sediment mass at 43 petatons, 43 petatons, of which 74% is marine, 26% is continental, and much of that mass is siliciclastic, and a much smaller amount is carbonate. So that's the Quaternary sediment mass. And if you take that 74% of the 43 petatons, well, then you divide by the length of the Quaternary, 2.6 million years, you get 12.2 gigatons per year. So that's the flux of during the Quaternary moving from place A to place B. Now, I've done this flux study a number of times, and I have to give you some warnings. This number here, 26 plus or minus 1 gigaton per year for Anthropocene flux, so since 1950, this number has been and will continue to change. So it is the interval average as I published in 2017. But if I will do it in 20 years from now, that will be a different number. And much of that 26 is coming from rivers. So it's 16 gigatons per year, of which 94% is suspended load and 6% is bed load. But even these ratios of suspended load and bed load, that's going to change over time. As we mine river systems, the amount of bed load has been and will continue to decrease. And right now, this is no longer 6% because of the mining for cement production, and I mean concrete production. The 4 gigatons per year in dissolved form, well, that has changed less radically than the particulates. Glacial contributions have been increasing. I'm sure Irina has told you all about that. But this ratio between meltwater and icebergs, that will continue to change too, because as you melt the marine glacial systems, get them back on land so they don't have an ice front in the ocean, you will decrease the amount of icebergs and you will increase the amount of meltwater. And then we have smaller amounts coming from wind that will increase with as winds increase with global warming. And as sea level rises, we will have an increase in coastal erosion too. So all I'm saying is that these numbers are in flux. Now, one of the great things that have happened in the Anthropocene is that we impound or sequester sediment behind dams. And in terms of large dams, we've sequestered about 3,155 gigatons of sediment behind dams. That's 65 gigatons per year. Now that's a lot of sediment. I mean, that's a huge amount of sediment. So if you were to look at the full Anthropocene flux, you have this Anthropocene marine flux that's delivered by natural processes. And then you have this marine interception rate, which is 74% of the 65 gigatons. And you add those two up, you've got 74 gigatons. That's a 600% increase over Quaternary sediment fluxes. And if you think that 74 gigatons per year is not enough, we then produce and mine another 160 gigatons of geological material. We have aggregates, 50 gigatons per year. Coal, 70, and its waste, 74 gigatons per year. We have cement production, 4.4 gigatons per year. We have mineral extraction, 27 gigatons per year. That all comes up to 160. You add that to the 74. Now you've got 234. That's an order of magnitude more flux of material being moved around Earth's surface than during the Holocene. And all of these create all sorts of crazy things, like the dams will then populate with reservoirs, surface water, where it never existed before. So this part of the picture of the Mississippi, all these lakes you see here are reservoirs. They're not natural. And of course, that's altering all sorts of dynamics in the Earth system as all over the world. And you've all seen the story about sea level lowering, where you have Jakarta, places of it sinking 4 meters over the last 35 years. That's because of pumping up of water. They don't have most of the population doesn't have municipal water supply, so they have to pump it up from beneath them, and they sink the delta. In Italy's case, the pole, it was methane in the mid 20th century. In Bangkok, in the sea level fall, or the land sinking there, that's largely from water mining. The Yellow Delta, where was I? Okay, well, humans, back to humans. We can sink deltas. We're very effective at that. And this little series of equations here, you have the Exner equation of aggradation minus erosion. And for most deltas, they should be growing at a certain rate. But in the Anthropocene, we're getting less sediment to the deltas. So that value has gone down. And because sea level has risen from its late Holocene, that value's gone up. Natural compaction hasn't changed because that's a natural system, but the compaction due to humans has really changed. And the tectonic signals, they haven't changed that much, so they're the same. But just those small minor changes can change how the elevations on delta can go from a positive value to a negative value. That's an Anthropocene story. So when you look at a movie like this, which is one satellite image per year, the Mississippi, and you just look at it and stare at it for a bit, I'll let it play a few times, you can see. So one of the ways I think that going forward, I'm retired, so this is all a talk to the younger folks here, is that there's some great big opportunities to do good science from a source to sink perspective and to play an important role in Earth system science and the Anthropocene stratigraphic studies. And I'm going to tell you a few of the ways that I've gone forward with. One is that I'm using climate discharge transport models. So by applying them, I can look at the hydrodynamics of the entire planet from a river point of view, and I can be looking at the behavior. There's things to learn about the natural system when you do that, but there are also ways of using it to look at how changes in temperature or changes in other fluxes that would impact source to sink efforts would really show up. So so how do we do this? So I'll click on that. So one of the ways is that you can look at, well, where are you getting departures from normals in discharge? So from year to year, you will have wet years and dry years. And during a wet year, you may find that most of the anomaly, positive anomaly, is in this area of the Ganges, or another year it may be down in here in the subcontinent. Well, if the extra water is going on to the most erosive zone, you're going to get more sediment than you would if the extra water that year, the wet year, fell on the less erosive parts of the. So that, I suppose, is an example of how you can use what are the impacts of climate and microclimate from year to year. Another way is I've been working with some colleagues, Jim Best, Sagi Cohen, and others, is to look at the impact of water temperature. And that's been very interesting because stream temperatures have quite a range around the world, which impact the fluid density, which impacts the kinematic viscosity, which impacts the particle settling velocity, which impacts the suspended bed material transport, which impacts the wash load. And so I've been using that to sort of understand the behavior of these river systems. And again, you can do it in both a natural state or anthropogenic state. So some of you have seen this slide where we look at the Yarlung Sangpo Brahmaputra river system flowing from behind the Himalayas and then into the lower Brahmaputra plain. You have a 134% range in temperature. You have a 15-fold range in discharge, and these both have an enormous impact on the transport of sediment. These models give you, and I'm just giving you a flavor for the models, they give you water properties along the length of a river system as an example. And you can see the changes in discharge, changes in stream velocity, temperature, fluid density, viscosity. And you can, in fluid density, you can even see how suspended sediment concentrations are impacting fluid density. You can then apply your favorite bed load, suspended load equations and start understanding the dynamics of that river system. And you could even be looking at, well, where are these temperature effects coming from, and what role do they play in the transport and deposition of sediment, fluvial sediment? So that, I'm going to end my talk here. That's it. It's just a quick overview to allow you folks to see, those of you that are left after that bombing, that source to sink investigations play and can play a very important role in Anthropocenic epoch studies. And Earth system science needs both source to sink and Anthropocene studies to really flesh out what's happening on our planet. There's lots of great science to be done. So I'll end it there. Thank you.
Thank you, Jai. And I'm terribly sorry about the accident. You know, this is the age. This is part of the Anthropocene event. So let's see how we can ask a question. Let me try. So let me enable the chat. And so maybe you can, if you have any question, you can try to type on the chat. And okay. Let's see if I can allow you to unmute. I just afraid. Let's try. Okay, let's try. You know, I turn on the unmute. So if you have a question, go ahead to ask any question. I'm pretty sure, you know, we have many questions for audience. So if you have a question, please go ahead. Jinping, go ahead.
I don't have a question. Hi, Jaia. Good to see you. It's been a while.
You too.
So exciting to see all those hackers to come in. Like I always said, only stars get hacked. Right? I just want to say hello. Good to see you.
Nice to see you too.
So anybody else? If you have a question, maybe you go to the participants and raise your hand. Oh, Bill.
Hi, Clark.
Okay, Clark, let you, Clark, go ahead to unmute yourself. Anybody have a question? Please unmute yourself.
Okay, everyone who looks at you know, future patterns looks out to 2100. Have you extrapolated your trends out to 2100 and have predictions for how all your parameters are going to be stacking up and ramping up over that time?
From okay, that's a really good question. So from an Anthropocene epoch study sense, you know, the focus has been, where does it begin? Has it begun? And where does it begin? It's not really about where does it end. But you can't do this kind of science without thinking about that. And so one of the things we've been thinking about is, well, what signals have happened already and how long will they last? So for instance, one of the greenhouse gases, carbon dioxide. So if we stop pumping out CO2, it's going to be around for about 100, the extra CO2 that's in the atmosphere, the anthropogenic CO2, that will be around for about 100,000 years before it gets cleaned up. So there's an example of a signal where people are interested in how long things will last. Another signal would be radioactive isotopes. So we've looked at, well, of the bomb isotopes, which ones are the long-lasting ones? Well, plutonium is an example that is very long-lasting. That'll last over 100,000 years. That are detectable with today's methods. So of course, it's a bit of science fiction what methods we have in the future. So yeah, we do this, but it's not the focus. You know, when we talk about a persistent pollutant, we often talk about, well, how long will it last? And so it does come up and it should come up, but it's for picking what we call a global boundary stratigraphic section point, GSSP. That's doesn't really enter those studies.
Okay, great. Any other questions? I can unmute yourself. Yeah, Robert.
Oh, hi, Jai. Good to hear you.
Good.
I was building on the point about the previous remark about where are these things going, because you made the point that, you know, we're interested in when the Anthropocene started, but from a sort of human perspective, I mean, dealing with all these issues, the trajectory is pretty important. So you've made the point that some of these things are very long lasting, but certainly things like population, the expectation is that some of the drivers are going to sort of stabilize and maybe even start declining. So we've got some interesting sets of behavior coming up in the future, I suppose. And of course, technology is evolving in all kinds of ways we don't understand and can't predict. Do you have any sort of thoughts on that, you know, about it's more of a comment, really, but anyway, your thoughts are welcome.
No, I'd like to address that, Robert. Well, first, it's lovely to see a friend or hear a friend. So nice to hear from you, Robert. Okay. So if you look at these drivers, and in all cases, I can't believe how they're so intimately correlated, these environmental parameters with the three drivers: productivity, energy consumption, and population. So the rate of growth may start to decrease and maybe in a couple hundred years level off. But it doesn't really matter, does it? When you have 8 billion people, whether it's 10 billion or 20 billion, and it's not growing very much, you still have 20 billion and their footprint. And so the Holocene has, from an Anthropocene perspective, the Holocene has on average 94 million people. And here today we're approaching 8 billion people. So for the things that are directly tied to it that cause global warming, let's say we solve global warming problem. We had energy sources that weren't pumping up these greenhouse gases, and we were all on renewables and all of that. The footprint of the humans is still huge. Even with the global warming side reduced, you still have all of the role humans have on from their dams, their sequestering of sediment. Maybe the dams are now going to have to be torn down in the 200 years from now, and all that sediment becomes flooded back to the coastal zone. There will be the dynamics of the Anthropocene will continue to be dramatic, even when you step away from the greenhouse gases. And the thing is, I don't think we're going to step away from the greenhouse gases because we are really hooked on things like nitrogen, reactive nitrogen, and fertilizer, which is a greenhouse gas when it's through emissions. And so that's not going to go away. And the reason I know that is because half of all the nitrogen in our bodies is from the nitrogen that we produce ourselves. And half of our food supply exists because of this reactive nitrogen. So there are some things that maybe global warming side of the story is not going to be very big in the future if we solve that problem. But many of the other Anthropocene drivers will still have huge, continually huge signals. Sea level will continue to be a problem, etc. So it's a good question, and I don't think it's all tied to greenhouse gases and global warming.
It's great. So any other question? You can raise your hand. Or...
Hi, Robin. So Robin, you had your hand up? I can't hear you though.
Robin, so let me see.
Enter the waiting room. Someone entered the waiting room.
Okay.
Thank you, Paul, for dealing with all of this. And thank you, Jack, for that wonderful talk. That was very interesting. I'm interested in a point you made in the beginning of your talk when you said how many new minerals had been made during the Anthropocene, and you said that they weren't synthetic, they were naturally made.
Well, they're not naturally made, they're humans made, but there's something defined as synthetic minerals, and which is separate from minerals that, this is really not my field, but when I've gone to their, the German website that holds the entire list of all minerals, they make a really distinction that the 180,000 new minerals that they've identified from human action, and it could be a reaction in cement, for an example, or something like that. It could be you put plastic in a cement to lighten it up and it creates something else. Those, they're not considering synthetic in that you are creating minerals under atmospheric conditions that don't exist on Earth and are played with in that sense. They have another database for those. They're focused on those that are occurring in our own human Earth system, even if it's from us.
Thank you for that clarification. That makes a lot more sense.
Hey, Joy, I have a question. So you talk about, I think, thank you very much. You know, even this morning, there's so many disturbance. So you give a fantastic, comprehensive, so far, this is the most detailed overview or review about Anthropocene, the change since 1950. So my question is, you know, the rapid change, even including CO2, now we have 416 or 17 ppm. So sea level, you know, temperature, everything. From sustainability development point of view, if this trend keep going on, how long do you think our human beings have to give up?
Yeah, you know, I have an article coming out in Nature's Communications in Earth and the Environment. We're approaching embargo time, so the article will be released shortly. Where I lay most of this out, and there's 17 co-authors of mine on the paper, so it's a major undertaking by leading scientists. And when we wrote it, to document some of which you've seen on this presentation, when we documented it, I personally felt like a war correspondent who's unfortunately having to report on a war, or in our case, the state of the planet. And it's not a good state. Yeah, I feel like a war correspondent. It's kind of sad. I think we have an existential threat right now with global warming.
Yeah, you know, the problem is really natural science is the one thing, the greedy, the human being. I mean, we are so greedy for our material need. This is somehow you see all the change in the last 70 years. So looks like I'm not sure we have any solution to change this trend or not.
Well, let me give you, okay. I'm retired, so you won't be seeing that much of me in the future. But I want to take this opportunity to say a few things. You know, I think that I don't want everyone in this audience to get depressed about the future, but you should get an understanding of magnitude and the magnitude of things, perhaps how long things take to change. And what it means when we are changing an entire, terraforming a planet, even if we don't mean to terraform this planet. I think you have to understand that many of the changes are not down at the individual level. Now, humans use plastic, and that plastic gets into the environment, and that's a very negative thing. That's an example of down to the individual level. But most of these things are not down to the individual level. Most of the greenhouse gases that are going into the atmosphere are happening in a few locations around the world of unbelievable magnitude. They're just really pumping out gases with little control. And those are the ones that we have to do something about immediately. But we should also be, as a society, thinking about, okay, we want to create a society that does hold a fair number of humans in a comfortable, sustainable environment. What does that mean? And I think if we work together as humans and we got out of the politics and we got out of the power struggles, we could end up with a world that's quite lovely and very positive. So don't turn yourself off simply because you've heard some bad news about the state of the planet. You know, work to ensure that sustainability is something that's sort of ingrained in all of us as we go forward, and work within the political system to say, no, we want governments that take this seriously, that will do something about it in a very proactive way, where our long-term future generations will have a life as great, if not greater than the one we have. We can do it, but we have to work on it together.
Fantastic. Thank you. And at least we still have hope. We need working together. So yes. Particularly based on science. And
bye, everyone.
Thank you, Jai, for this wonderful talk. So I guess many of us, we need to go back to watch your presentation slowly because you have so much information. Each slide is a review paper. So I'm sorry for the audience. I will re-edit, I will clean a little bit, trim the video and make it much professional, and it will be show up on the YouTube. So please go back to watch the YouTube. Once again, next week we have two more presentation. Edward Tip from University of Cambridge. He will talk about the silicate weathering, and also Edward Anthony from France. He will talk about river delta longshore segment transport, Amazon, Mekong, Irrawaddy, and the Niger River Delta system. So please mark your calendar. Please come back next week. I will apply more security control over this Zoom meeting conference. And thank you, Jai, very much. Thank you all the audience for your bearing the little bit the bombing, hacker bombing. So this is the world we are living now. So thank you. So I'll see you next week. Have a good weekend. Bye-bye.